Welcome back, students. In this particular lecture, we are going to discuss more about higher quality current mirrors. In this process, I wanted to also show how the innovation happened, how each time there was a limitation that was discovered, then somebody else came in and invented some new ideas and overcame those limitations, and the process continues. This particular example I'm going to show you is a very good proof of that. So last lecture we talked about cascode current mirror, and one of the limitation of the cascode current mirror was let me draw the cascode current mirror. What was the issue with this current mirror or current source? Of course, one issue that we talked about last time was the output voltage V out cannot be. It's a large number. It's VT plus 2 VD sat. That's what we discovered, and that could be a problem if you're trying to do a low voltage circuit, which is specifically 1 volts or 1.2 volts. This is VDD. Okay, so the next revelation or next invention that came along was take this circuit and modify it slightly, and let me show you what the modification was. So this is what this was the modification, which is to connect this and like this. Okay, and then this particular voltage is biased using V bias. Now let's analyze this particular current mirror, and it's called low voltage and high swing cascode current mirror. Okay, let's label everything. This is V out, this is I out, this is transistor M1, M2, M3, M4. Okay, all right. So what is R input here? Okay, so the R in, and this is the R out. What is it? So what I would like you to do is just use a small signal analysis for this particular circuit and prove it to yourself that R in looks like 1 divided by GM1 approximately. Okay, so this is something that you have to do, prove it yourself using small signal analysis. The voltage V bias is chosen in such a way that transistors M1 and M2 are both in saturation. What that means is VDS for both M1 and M2 is equal to VD sat of the transistor. At least VD sat. I mean, you can keep it slightly higher, and generally that's what you do when you do the design. Okay, so VDS1 equal to VDS2 is equal to VD sat minimum. Okay, so if voltage at these points where I'm showing the arrow, that's equal to VD sat, then you go from that point one level up, from this point one level up. And what is that transition? That would be equal to the VGS of either M3 transistor or M4 transistor. So you can choose V bias is equal to VGS3 plus VD sat. As long as you keep V bias, this particular voltage, greater than VGS3 plus VD sat, then transistors M2 and M1 will be in saturation region. Okay, but minimum you need to keep VB equal to this. So then what this means is I can, this would be equal to VT plus VD sat plus VD sat. So you want to keep VT plus 2 VD sat approximately, something like that. So V bias should be approximately that value, and you can choose another small current source and derive this voltage separately. That we can look at it later on how to do that. Okay, all right. So once you do that, then what will be? So now we know that the arrow, the new arrow, the yellow arrow I'm showing, this is what is the potential at that point is going to be VD sat. And now the V out. What's the minimum potential at V out that we can have? So we need to have at least one more VD sat here, okay, across this, and here is another VD sat. Okay, so now you can see that V out minimum, we can get it equal to VD sat 4 plus VD sat 2, you can approximately say 2 times VD sat. If VD sat is 200 millivolts, then this can be approximately 400 millivolts. Much better situation compared to the cascode current mirror we just did in the previous lecture. Okay, so this can be used when you are operating from 1 volt supply, 1.2 volt supply, and you will have enough headroom to make use of this current source. Okay, all right. Now, other property of this particular current mirror is the current value IREF here. Okay, this IREF is flowing through M1 and is developing a VGS. Okay, VGS. Now, the value of the VGS, if everything is designed correctly, is based on VDS of VDSAT. Okay, so if you look at transistors M1 and M2, they have exactly same VGS and also exactly same VDS. Just because of that effect, you can say that the lambda effect or the channel length modulation effect, you're taking care of that. In the previous one, you could end up in a situation where in a simple current mirror, the VDS could be different, and as a result of which you have the lambda effect coming in. In this particular case, for the core transistor M1 and M2, the current will be almost identical between the two transistors because they have same VDSAT or VDS across them as well as the VGS. So the two currents are almost identical. So you get very good copying between the two transistors. Okay. So what's the disadvantage of this current mirror? As I was telling you, we are developing one idea and then finding the problem with it, and then we try to develop the next idea. So this particular current mirror, the high swing current mirror, was, by the way, invented by my friend Joseph Babnizad, and then the next invention came up, which is to how do we kind of take care of this V bias? Because to develop V bias, what I need to do is, technically speaking, I need to have another current source going into another diode transistor, and I need to kind of connect it this way, and I need to play with the W by L of that transistor to get the VB, which is equal to VT plus 2 VDSAT at least. Okay, so the next invention that came about to improve upon this is how can I get rid of this VB? Okay, so follow my train of thought, and that particular one is the current mirror with a smart biasing. Okay, so in this particular case, what you can do is you can draw a current source and you can draw a resistor, and here are your, let me redraw this just a little bit differently. Okay, and then you have, this is ground, and from the previous part, what we did was we connected it like this, all right, and then this was M1, M2, M3, M4, okay, and what is the voltage V bias that we needed? V bias we needed was equal to VT plus 2 VDSAT. This is your IREF and this is your VDD. Okay, so what is the voltage at this particular point, which is, let's call it with an arrow right here. Okay, that would be equal to plus minus VGS. Okay, and what is VGS? VGS equal to VT plus VDSAT. Okay, so this would be equal to VT plus VDSAT. What I can do is I can insert a resistor here in the IREF, and then I can connect the circuit like this. So this is something V bias I wanted to generate using a separate circuit, but just with a single resistor I can connect the V bias to the other side of the resistor. If you look at this, if you just look at the resistor, and this is your one part and coming down, and this is the resistor, this you would like it to be VT plus 2 VDSAT, and this value is VT plus VDSAT across the resistor. Okay, it would be pretty obvious that what you would really like, that is the voltage drop across the resistor should be at least VDSAT, and if you can satisfy that, then you can easily generate the V bias without having a extra stage. Okay, so the key point is the voltage VB, the bias voltage VB is generated using IREF. So the design equation for this will be let's see, so we have VGS 1 and VB. So design equation is the VB is equal to VT plus 2 VD sat. That's what we wanted. And if you look at R, which is the voltage drop across this, that is equal to VB minus VGS1. Okay, so this is VB and this is VGS1 as we see. So let's substitute here. VB is equal to VT plus 2 VD sat. And what is VGS1? VGS1 is minus VT plus VD sat. So this will be minus VT minus VD sat. Okay, so this would look like VD sat. So that would be our design equation. So resistor value you can choose will be equal to VD sat divided by I. Again, these are like the minimum values. In a typical design, you would keep some margin so that over process temperature variations, you always stay in saturation. So using the equations, we are figuring out the minimum values. You would kind of keep the drop higher than, or keep some margin of maybe 100 millivolts so that it's you're always safe. This is kind of a way to smartly bias the high swing cascode current mirror. What are we doing here, right? I'm showing you these different pattern of circuits. I showed you a simple current mirror, I showed you cascode current mirror, then we looked at high swing cascode current mirror, then we had looked at smart biasing. So these are the patterns. When you open up a schematic or a very complex schematic, these are the patterns you can identify very quickly, and you can tell, oh, this is a current mirror, this is this type of current mirror. And there would be obviously a reason why people are using certain connections, and I'm kind of exposing you to these patterns. And of course, the nature of this class is I cannot expose you to all the patterns, but I can expose you to few patterns so that you're able to explore more complex patterns on your own. Okay. All right. So, so far we have now worked on MOSFET current mirrors. And as you can tell, in the previous lectures, we always dealt with bipolar transistors first, and then we dealt with MOSFET transistors. In the current mirror case, I wanted to do the MOSFET cases first, and now we are going to do the bipolar cases. And we can see why I am doing that slowly. Okay. All right. So the next topic, as I said, we are going to discuss is bipolar current mirrors. Bipolar current mirrors, they come up with their own issues, and I'm going to show you how, those issues were resolved one by one, and you can see the similar progression there. So the simplest bipolar current mirror, since we have done a MOSFET current mirror, we can draw it as follows. If you look at this current mirror, again the VBE for the two transistors is same. So as long as the transistor Q2 is in active region, the current should be same or scaled according to the ratios of the areas, emitter base junction. Okay, so the key condition is going to be the VO min should be greater than VCE sat of the transistor Q2, which is approximately, as we say, 0.3 volts. If you look at the ratio of the currents, I0 divided by RF. I0 is the transistor current flowing through Q2, and RF is flowing through Q1. So that ratio will be equal to IS2 divided by IS1, which is equal to basically area of emitter base junction for Q2 divided by same for Q1. Here key assumption is we are ignoring base current, or we are saying that beta is equal to infinity. So this is the first order analysis which shows that the current gets mirrored. And let's say I want to get 1:10 ratio, then if this is 1x and if this is 10x, then you will get, all you have to do is have area of the emitter base junction which is 10 times larger for Q2, okay, to get the 10x current. All right. So now kind of let's dig deeper and see what's the effect of transistor beta, finite beta. Let's draw the currents exactly as they're flowing through this. Let's say the current flowing through transistor Q1, okay, is IC1. If IC is the collector current, then we know how much current is flowing through The base will be IC divided by beta. That's bipolar transistor basics that we learned. And how much is the emitter current will be here? IC times 1 plus 1 divided by beta. So the two currents sum up together to give you the emitter current. The same thing would be true on the other side. So you would also be conducting IC divided by beta on this side, and assuming the two transistors are exactly same, Q1 and Q2 are identical, then the current flowing through collector will be IC, and you have IC over beta over here, and this will be IC 1 plus 1 over beta. However, the key point here is this additional current, which is 2IC divided by beta, has to flow. And it has to come from your IREF current. Okay, all right. So if you look at this as a black box, then on the left side you're putting current IREF, on the right side you're getting IC out. If you look at IREF, that is equal to IC plus 2IC divided by beta. So all I'm doing is Kirchhoff's current law. IREF is here, and here is your IC, and this one is your 2IC divided by beta. Okay, all right. So then this is equal to IC 1 plus 2 divided by beta. I output is equal to IC is given then by IREF divided by 1 plus 2 over beta. What this is telling you is you have a certain amount of error due to the transistor beta, which is what is shown over here. So for example, if this was beta was 100, then you will get the output IC will be 100. So 100 would be this. If beta was 100, then this would look like 1.02. Okay, reciprocal of 1.02. That would be the error that you will get. Okay, so you will get kind of 2% less current at the output. This was a case when Q1 and Q2 are identical. Now, if Q1 and Q2 are, you want it to be scaled value. So, for example, let's say Q2 is M times Q1, which means that the emitter base junction area of Q2 is M times the emitter base junction of Q1. Then you will get, we expect M times current, M times IREF current to be flowing through the output. Unfortunately, because of the base current, what you would see is you would see I out divided by IREF. That would be the same as IC divided by IREF, and that would be equal to M divided by 1 plus M plus 1 divided by beta. So in this particular case, you can see that if M equal to 1, then this ratio approaches the one above. Okay, and if you had ignored the effect of this part, then you would just get M times scaling. Okay, all right. So here is a way to analyze the effect of base currents in this particular current mirror. Okay, and what are the other important things that we have to worry about? What is Rin? Rin is equal to 1 divided by GM1. Rout is equal to RO2 of the transistor of this particular transistor, which is equal to VA divided by I0. So this is your early effect that you have to worry about. So as I told you, when you compare bipolars and MOS, in case of bipolar, you are stuck by the early effect, and in case of MOSFETs, I have a control by changing the length of the transistor. I can control what kind of channel length modulation I can get, and the early effect we can control. In case of bipolar, you have a fixed early effect, and generally they're good. So that's what you get. Okay, so if you take into account the effect or the early effect, then similar to the MOSFET case, if you remember, in the MOSFET case we had this 1 plus lambda and the difference in the drain voltages. So similarly here you can have difference in the collector voltages, and instead of lambda you will get reciprocal of the early effect. Okay, I'll write the equation and it will become obvious. Okay, so I0 divided by IREF, M divided by 1 plus M plus 1 divided by beta. Okay, and along with that you will have this factor 1 plus V0 minus VBE divided by VA. this equation you may get surprised, but let me explain it to you. This part is due to the one in the box is due to the base current effect. And if you look at this part on this side, on the right side, if output voltage, which is at this point where I'm showing the arrow, if it's exactly same as VBE, then the two transistors have exact same VBE as well as VCE. Okay, so the effect of early effect will go away, and that's exactly what this is showing. If V0 equal to VBE, then the early effect goes away. All right. However, if the collector voltage is not the same for both the transistors, then you will see an impact of early voltage, and that's what you see with this equation. Okay. As I said, one of the issues with this bipolar current mirror is the base current, right? And base current gives you this 1 plus 2 over beta type of error. Obviously, how do we fix that? So here is the next circuit which fixes or attempts to fix that problem, and follow my train of thought. And the error was coming in because this 2IC divided by beta that I had to support from the original source. So now what I can do is you can insert a bipolar transistor over here. The bipolar transistor that we have inserted, the transistor Q3, 2IC divided by beta is its emitter current. Base current will be divided by the beta of that transistor, right? So in this particular case, it will be beta plus 1 because we are talking about relationship between emitter current and a base current, not collector current and base. So if you're looking at ratio between emitter current and base current, there is always beta plus 1 effect, not beta effect. Okay. So what you will see is 2IC divide by beta and divide by beta plus 1. So that would be the error that we have to support through IREF. And so in this particular case, you can write an equation. IREF will be equal to IC plus 2IC divided by beta multiplied by beta plus 1. Now we can rewrite the equation which is equal to IC 1 plus 2 divided by beta times beta plus 1. Okay. And this IC is the I out that we expect, and this is your V out. I0, this I0 which is equal to IC, and I0 divided by IREF will be equal to 1 divided by 1 plus 2 divided by beta and beta plus 1. Okay. And we can now approximate that, hey, beta and beta plus 1 about the same value. So you can say that this is equal to beta, 100 or 100 plus 1, which is 101, is same as 100, close enough. So we can say that I0 divided by IREF is approximately 1 divided by 1 plus 2 divided by beta square. Okay. So here is a interesting thing. Earlier it was beta, now it's beta square. So you can see the effect of, we are reducing effect of base current by an order of magnitude. Okay, so this circuit works very well. It's very commonly used to reduce the effect of base current. So this particular current mirror doesn't improve your output resistance, right? You don't have a cascade part here, because if you do a cascade, then you still have to worry about the base current. In case of the MOSFET, we don't have to worry about the base current. So we could just do cascading and increase your output resistance as much as you like, and modify some conditions to improve the output voltage swing. Okay. So in case of bipolar, one of the early current mirrors which was invented is called Wilson current mirror. So in the Wilson current mirror, let me draw it first and then explain it to you. So let's analyze this particular current mirror. Since the base emitter voltage is the same, the collector current for both these transistors will be same. Let's assume that first, IC. Okay. So now I have the base current which is going in this particular branch will be 2IC divided by beta. This is the same analysis that we did last time. Okay. And then the current which is flowing through the emitter of Q3 is going to be IC times 1 plus 2 divided by beta. All right. So then we can look at the base current over here. That's going to look like IC. All right. And then you will have, again, you're going to divide it 1 plus 2 divided by beta, and then you're going to divide it by beta plus 1. So the reason, again, you might confuse yourself why sometimes I'm dividing by beta and sometimes I'm dividing by beta plus 1. So the relationship between collector and base current is beta, but relationship between emitter current and base current is beta plus 1. Okay. So that's why we have beta plus 1 here. So whatever is the emitter current here, okay, that gets divided by beta plus 1. And that's what you have as a base current. Now we have the emitter current here. The collector current will be I0, that will be equal to IC, okay, and it will be 1 plus 2 divided by beta, and then you multiply that by beta divided by beta plus 1. Okay, that's the relationship between collector current and emitter current. Now let's figure out what's the relationship between this IREF and this I0, because that's the level of error that you're going to have due to the base current. And you will see certainly that the Wilson current mirror offers some advantage here. So let's go through that. And then I0 is equal to this whole number right here. Okay, I'll rewrite it again. IC, and then 1 plus 2 divided by beta, beta divided by beta plus 1, something like that. So we can take ratio of the two currents, which is I0, which is output current, and input current is IREF, and you can convince yourself that this ratio is going to look like 1 plus 2 divided by beta times beta divided by beta plus 1. All right, and then multiply this by beta plus 1 and divide by beta plus 1 plus 1 plus 2 divided by beta. This is just algebraics based on these two relationships, and I would like you to go through it yourself, and you can convince yourself then this is going to look like beta plus 2 divided by beta plus 2 plus 2 divided by beta, and this we can further approximate as 1 divided by 1 plus 2 divided by beta and beta plus 2, something like that. And this you can further approximate as 1 divided by 1 plus 2 divided by beta square. So we get the same effect of reduction in effect of base current, the beta square effect, which is great. However, the real advantage of this particular current mirror is the output impedance, output resistance, R out, okay, and this R out is equal to beta 3 times RO3 divided by 2. Okay, so you kind of get like a cascading effect over here. Okay, and this particular analysis I would like you to refer to Cedra and Smith, page 505. Really quick analysis that you can go through and convince yourself that this is what happens. A little bit of algebraics you have to go through and convince yourself. But the key point to remember is the beta of Q3 helps you, kind of multiplies the R out. Okay, so you have a beta multiplier to your R out. So that's about Wilson current mirror. The next current mirror I'm going to tell you is was invented by it's Bob Widler, and it's called Widler current source. One of the issues that you have in a bipolar based designs. Imagine you don't have any MOSFETs. So this is coming when in the pre-MOSFET areas, and you wanted to develop like really small current. Okay, let's say you needed like a 1 microamp or 10 microamp current. Then it was a little bit hard at that time because supply voltages were high, and along with that, so let's say that I wanted to develop 10 microamp current source. Okay, then if the supply voltage is 5 volts, then you would have 5 volts, and you would put a resistor, and then you would put some kind of VBE. Let's say if you did that, and All of you know what the VB value is. Let's say 0.7 volts. So then 5 volts minus 0.7 volts divided by, I want 10 microamps of current. That will be equal to, this is our R value. That will come out to be something like 430 kilo ohms. Okay. So this is a large value. So to generate small current sources, you have to use large resistors. So with Widler's current source, you can overcome that problem, and with small value of resistors, you could generate really small currents. So let's go through how you can do that. And the circuit looks something that you will see it again and again in future during when we are looking at reference circuits. Okay. All right. So what is VBE1? VBE1 is equal to VT ln IRF divided by IS, and VBE2 is equal to VT ln I0 divided by IS. When we look at the potential across this resistor RE, what is that potential? Is going to be VBE1 minus VBE2, and that is equal to VT ln, and when you take a difference, you'll see it's IRF divided by I0, and that is equal to, again, VBE1 minus VBE2 will be equal to I0 times RE. So the defining equation becomes really simple for this particular current mirror, is I0 RE is equal to VT ln IRF by I0. What's so special about this this particular equation, right? So if you look at this particular factor over here, this particular factor is in the ln. Let's say that somewhere in my circuit I have 1 milliamp available or higher current available, because higher currents are easily developed. You can generate using this bipolar circuit by using a smaller resistance, right? So what you could do then is the key factor that you get is ln effect. So the point here I'm trying to make is, let's say if you look at ln of 100, and that comes out to be, let's say, 4.6. If you look at ln of 1000, okay, that comes out to be 6.9. The factor inside the bracket is in ln, right? Ln kind of compresses that number quite a lot. So in this particular case, if it's 100, it's 4.6, and if it's 1000, it's 6.9. You could kind of take this circuit, and you can derive your small current source really quickly with a small resistance value. So let's take a numerical example, and that will make it very clear. What I would like to generate then is a given IRF of 1 milliamp. Let's say IRF is equal to 1 milliamp, then can I get, what would be the value of resistor to generate I0 of 10 microamps. 1 milliamp to 10 microamp, you cannot just use a current mirror to scale, right? Because that's factor of 100. That means you will have to put 100 devices and match them really well and all that stuff. So that's not practical. If you just wanted to generate 10 microamps, then you will end up using a large resistor. So that uses a lot of square footage on the chip. So the Widler current source allows you, using this ln effect, to generate small currents in an area efficient manner. That's what it is. Okay. So we can see quickly in this particular example, if I have if IRF is equal to 1 milliamp, then my equation becomes I0 RE is equal to VT ln of IRF divided by I0. We already said that I have given IRF equal to 1 milliamp, and this is equal to 10 microamps. So this ln part becomes equal to 4.6. Okay. So now we can say that, hey, what is the value of RE? Value of RE will be VT times 4.6 divided by I0, which is equal to 10 microamps, which is what we want, right? So then we can see that it's 26 millivolts multiplied by 4.6 divided by 10 microamps. And you can quickly see that the RE comes out to be very reasonable number, which is like 11.96 kilo ohms. The Widler's current source allows you to scale currents to smaller values accurately using this property. Okay, so again, once you see this Whittler current source, you will be able to tell what's really going on. The intent is to create a very large scaling ratio of currents. So on the left side, if there is a 1 milliamp flowing, on the right side you have only 10 microamps flowing. So you got a factor of 100 with such a small area on a chip, right? So that's a major advantage of this thing. Other advantage of this particular circuit is, if you remember, you get effect of cascading due to transistor Q2. Okay, this transistor Q2 cascades the resistor RE, and if you go back a couple of lectures, then you can convince yourself again that the R out is going to be, if you look at R out, so the R out from the previous case is 1 plus GM of this transistor multiplied by RE parallel with R pi and multiplied by R out. Okay, it may seem like it's a lot to remember, but very similar to MOSFET case. In the MOSFET case, you get multiplied by GM R out. In this case, you have GM R out multiplication. However, the RE has the R pi looking this way also in parallel. So you have to take that into account. And this we have done it before. So this is the advantage of, this is another advantage of Whittler current source, that you can increase the output resistance of the Whittler current source. So this kind of completes introduction to all variety of current sources, current mirrors, which happen, and which we can do using a bipolar transistor as well as MOSFET transistors. And you can pick and choose depending upon your application, and pretty much advantage and disadvantage of each one of them. Now, one particular thing that I would like to mention is, why is it that we are always interested in a large R out? So if you look at the current mirrors, right? Let's say this is one box, this is current mirror 1, and here is another current mirror. Okay, CM2, and we connect them together. The output of one current mirror is going into the input of other current mirror. Let's analyze what happens in that particular situation. So we will just take a MOSFET example in this case. Here is my current mirror, and here is another current mirror, and then I will draw another current mirror here. One critical thing to realize is that, let's say I decide to put in a signal current I, small I here. I would like you to, I'll give you 30 seconds to think about it, or you can pause the video and think about it. What would be the direction of current coming out of the first current mirror? Pause the video right here and think about what would be the direction of the current. Would the current be flowing this way, or would the current be flowing this way? I hope you have thought through this, and let me kind of take you to the answer, which is how do you analyze this, right? So what is the current flowing through M1? The current flowing through M1 is going to be I plus small I, okay? And that current will develop the voltage VGS across this. So what should be the current flowing through M2 then? Answer would be fairly straightforward. It should be I plus I. And if the current I on the top and I plus I on the bottom, then we need to have current flowing in this direction, which is like this. Now, when you look at this particular structure, you can see why it is called a current mirror, because it's like, the current going in, and then it's like a mirror, it's coming out on the other side. I mean, it's like in a mirror fashion going out there, right? So what is the current flowing through this circuit now? The current flowing through this circuit will be I minus I, okay? And hence, what would be the current flowing through the transistor M4 will be again I minus I. All right. And now you can see that there should be current I which should be going out. Now the reason I'm going through this simplistic analysis for you is I would like you to think about this particular interface right here, partition it. When you look back on this side and when you look to the right side, what do you see? What do you see on the left side is you see a current which is going in this direction, which is I, and you have an output RO1 of the, or let's call it RO left. RO left is the output impedance or output resistance of the current mirror on the left, and that is being connected to the current mirror on the right. And where what is the input resistance looking into the current mirror on the right? That is going to look like 1 divided by Gm of transistor 3. Now you can quickly see the current which will flow in this branch will have some error just due to the output resistances. Okay, part of the current will flow through RO left, and only part of it will flow through the input resistance of the right side current mirror. What we want is we want all the current, this I, to flow through the next stage so that we get accurate current mirroring. That's the reason what we want in a current mirror is your input resistance should be as small as possible, 0, that's desirable, and your output resistance should be as large as possible, infinite if it's possible. Okay, so of course none of those conditions are possible. So what you want to see is input resistance should be something like a GM type of transistor, or I mean, there are other cases where you can get a multiplier effect over there also, so that you can reduce the input resistance using feedback. But that we will take care of it when we learn feedback. Okay, so the key thing I want you to remember is the nuance of output resistance and input resistance, specifically when you are cascading current mirrors, and you will end up having errors due to the these resistances which are there when you are representing these current mirrors. Okay, and we will stop right here, and in the next lecture we will move on to a different topic.